Yes, Jatima, you can introduce the speaker.
Shall we start? Yeah. Okay.
Yeah. I think it is better to start.
Okay. Okay. Welcome everyone. I welcome you all to this SGTSI monthly lecture, and it's my pleasure to actually host this event. And today's speaker, I'm absolutely delighted to introduce Dr. Pritam Nasipuri, who is a senior colleague of mine from IISER Bhopal itself. Dr. Nasipuri did his bachelor's and master's from University of Calcutta and a PhD in geology from Indian Institute of Technology, Kharagpur. And then he did his postdoctoral research at University of Torsmo in Norway. And then he joined IISER Bhopal in October 2012. Currently, he is working at IISER Bhopal as an associate professor. His specialization is mineralogy and metamorphic petrology, although he does quite a bit of structural geology as well. So with this brief introduction, may I request Dr. Nasipuri to deliver his talk, and he is going to talk on deformation of plagioclase, natural and experimental results. Dr. Nasipuri, over to you.
Thank you, Dr. Jyotirmoy, for your generous and kind introduction.
Dr. Nasipuri, if you don't mind, can you switch on your camera as well, so that at least for some time, so that people can see you?
Oh.
And yeah, and then you can switch off after a while.
Yeah, because I am doing it to save bandwidth here.
Oh, okay, then it's fine.
Yeah, because you know our net.
Sure. Okay, go ahead.
Okay, so is it visible?
Yeah, it's visible. You are clearly audible. You can just put it to the presentation mode and start.
Okay, so thanks to Dr. Jyotirmoy for this introduction and for giving me the opportunity to present the results or some of the works which I did during my PhD and my postdoc studies during the deformation of plagioclase. So today I am going to mostly discuss on the deformation of the plagioclase, and there were a lot of experimental results is already available in the literature. So how to correlate that results with the natural examples. And the outline of my talk is as follows. First, I will discuss some of the basics of deformation mechanism. And most of you are aware of these deformation mechanisms. And needless to mention, the concept is taken from Professor Tulis and On's group and Professor Holger Sunich's group, who formed the baseline for deformation studies. Second, as a mineralogist, I will discuss some of the importance of feldspar, why feldspar is so important. And finally, examples of feldspar deformation that will come from the annotocyte complex, which is mostly the purest source of feldspar. And finally, I will conclude with the future directions, how we can integrate the igneous metamorphic petrology and rock deformation rock deformation. So to begin with deformation mechanism, first to study the deformation mechanism, what I learned from my PA postdoc is that microstructural observations, what we got here should be commensurate with the experimental results, as well as the microstructure must be stable enough to survive the subsequent deformation and or heating event. If those two conditions holds true, we can divide the microstructure deformation in two processes that all of we know. The brittle deformation, which is usually the low temperature process, and the ductile deformation, which is the high temperature process. In the low temperature brittle deformation, how to identify mostly fractures that occurs across and between the grains, and the resulting fragments move to each other and losing the grain to grain contact. There are a lot of examples, there are a lot of examples by Professor Thalis group, and they did a lot of experiment on the brittle deformation of feldspar especially, and for the quartz there are other authors. Again, for the ductile deformation, which is basically high temperature process, the grain changes their shape or move relative to each other without fracturing. This is very important because if the grain can change their shape without fracturing, it can store an enormous amount of strain within it, which can lead to which can lead to some other disaster events later. Now, today I'm going to discuss with the ductile deformation. Again, I must say this is most of the things are concepts are taken from Professor Olga Stoni's concept, which and they have discussed three types of creeps. First one is the dislocation creep, all of you know it, where the change of the grain shape is occurred by crystal plasticity, and how to identify with deformation twins, bands, and deformation lamellae. And these features has been quoted by several authors, especially it is summarized in Varner 2004 to identify the dislocation creep in feldspar, olivine, and other minerals. The other extreme, what we have is a diffusion creep. Diffusion creep occurs of material through around the grains called diffusion creep. Here, what happens? The grain size should be extremely small, equant, and there should be a chemical zonation. Apart from these two, another grain diffusion creep, another flow is there, which is known as granular flow, which mostly occurs between grain size of 1 to 10 micron, where relative movements of the grain and grain boundary sliding occurs. Now, if we see the strength of the rocks with these three basic mechanisms, the dislocation creep to the diffusion creep and the granular flow, the change in the deformation mechanism decrease the strength decrease the rock strength. This is very, very important concepts. And if we compare the starting material for diffusion creep and dislocation creep, most of the granular flow diffusion creep occurred in a fine grained material. That means where the grain size is between 1 to 10 micron, whereas the dislocation creep grain size is mostly greater than 10 micron, and usually it is 100 micron. So there is a basic difference between the dislocation and the diffusion and granular flow, as the change in the dislocation creep to the diffusion creep will decrease the strength, as well as it will occur in the fine grained material. But today presentation, I will show that although this is experimentally proven, we can have diffusion creep in larger feldspar grains, which are mostly 100 micrometer in size. Again, just to repeat one more important concept, that is recovery, where all the processes, these processes which produces the deformation, attempt to return to a crystal to the undeformed state without the formation of the boundaries. So here, what is important is that we will not produce any new grains. As defined by Varnan, Tullis, and many others, the recovery can be dynamic, which occurs during the deformation, or it may be a static recovery, which may be occurs after the deformation. And here comes to a concept of strain hardening and strain softening. Now, after this, again, it comes to a concept of recrystallization, where part of the work I did with Professor Stuni, which indicates that the aggregates of the new grains that are strain-free and therefore capable of continued deformation. That means recrystallization is the process which are produced and capable of continuous deformation. And in nature, there are three types of recrystallization mechanism. First one we can say is progressive subgrain rotation, where dislocation accumulates in the subgrain boundaries. I'm repeating it, then I will show you the examples. Boundaries are progressively increasing their complexity and misorientation. So usually study says 5 to 15 degree misorientation is most common for these cases. Again, the second process is strain-induced grain boundary migration, which is occurring higher than the temperature than the progressive subgrain rotation, and this is known as traditionally slow grain boundary migration, which okay, I will slow down, no problem. So strain-induced migration, which induced Slow migration involves differential migration into different spaces. Now, another the most important is the great traditional or fast grain boundary migration, which is basically the high temperature process, where more pronounced from a grain boundary bulging that occurs during recrystallization. Some of you, those who are doing research in this area, although I am not an expert in this area, there was one paper by Steve Petal which described the deformation mechanism of quartz. Similar way, subgrain rotation, strain-induced grain boundary migration, and fast grain boundary migration. Similar way, the deformation in the feldspar also can be defined in a three-way. Subgrain rotation, which is basically strain-induced process, then strain-induced grain boundary migration, and finally, we'll have the high temperature grain boundary migration process which is from the where most pronounced from a grain boundary bulging that occurs during the recrystallization. I hope this part of the things are mostly clear to all, clear, and this is a repetition, and all of you are expert in this field. Now, to come to the point why feldspar is so important. If we see this is I took from the encyclopedia diagram. If we see the mineral abundances, which is basically my expertise, the alkali feldspar and the plagioclase feldspar constitute 49, nearly half of the Earth's crust, whereas quartz, pyroxene, amphibole, mica, clay, and other minerals constitute the rest. That is why plagioclase is so important to study, to know the natural processes that weakens or deforms a rock. This is the reason we are studying the plagioclase. Now, this is again the diagram which was covered by in all the classes. Plagioclase has three end members: orthoclase and microcline, which is known as the potassium feldspar. Sorry, we have albite, sodium member, and annotocyte. Now, alkali feldspar and plagioclase feldspar crystallize in different systems. So they have a different mechanical crystal properties and mechanical behavior, as well as the alkali feldspar constitute 12% and it's mostly found in the granite, whereas plagioclase feldspar is mostly found in the part in the granite and into another rock called annotocyte, where it occurs in its purest form. So that is the reason I just did my PhD and postdoc on the plagioclase feldspar, and this is a rock which is called annotocyte. Annotocytes, some of you may know, is very important because it occurs only in the two times during the art, during the Archean times and during the Gondwana, during the Greenvillian orogeny time. And the annotocyte model is as follows. Well, now here it comes to crystallization of plagioclase feldspar will lead to a rock annotocyte and
Dr.
a resin.
Nasipuri, we briefly lost you for like half a minute. Can you just repeat this slide once more?
Annotocyte.
Yeah.
Yeah, it was network connection.
Yeah, I think so.
Okay. So annotocyte is a very important rock in the evolutionary history of the Earth. Annotocyte was emplaced during two times in the geological history. During the Paleoproterozoic time, and once during the Neoproterozoic time, during the Rodinia formation. So in annotocyte, the general model is very simple, and here I will introduce a bit of igneous petrology concept. This was taken from the concept from Oswald 2004, where high alumina basalt is the primary material. This is thus like the ocean basalt with fractional crystallization of enriched olivine and pyroxene. This is the primary products according to the Bowens reaction series, which crystallize at more higher temperature, will lead to a magma which is enriched in calcium, aluminium, because magnesium is going out of the system. Now this calcium aluminium enriched magma can again crystallize once this is coming up to forms the plagioclase feldspar. And once the plagioclase feldspar is getting crystallized, it proves a residue, leaves a residue which is high strength, high field strength element, and sorry for the typo mistake, and rare earth element enriched magma. So this plagioclase feldspar floats because this is low intensity and it forms the feldspar anorthosite. So this is a schematic diagram of the same. While in the upper mantle lower crust interface, this phenomena usually occurs. That means in a brittle ductile term, we are dealing with the ductile deformation again. So the Mg cumulates are shown in red terms, which is going below, going below because these are the dense, and the lower crust feldspar liquid mass is coming up. And now I will show you the results that depend on this amount of melt present, or if the feldspars achieve grain to grain contact, a wide variety of microstructure can be produced, which often do not agree with the experimental results. So in India, you know that proterozoic anothocytes are mostly hosted in the Eastern Ghat granulite belts. In the Eastern Ghat granulite belt, there are 6 well-reported, well-studied anothocyte complex, which is among which Bolangi is the most studied because it's very large in size, nearly 400 square kilometer, and this was studied by several authors. So this is a geological map of the Bolangir anothocyte complex. You can see this as a roughly circular or elliptical in shape, and there are very associated rocks, which is the Eastern Ghats typical country rocks, metapelite, calc-silicate, and quartzofelspathic gneiss. Now I would like to mention, point your attention here. You can see there are some dark rocks, dark bands. These rocks are called, and these are called ferrodiorite or FTZ, and traditionally these rocks are considered as the residual melt for during anothocyte crystallization. Now this residual melt has a significant importance in bearing on the rheology of the rock. So first one from the structural map, that in the central part the anothocyte is mostly massive. There is no such foliation, whereas in the marginal part there is a outward defined outward defined foliation is observed. Just to solve this riddle, what I did is first I measured the grain size, and this was published in Nasipuri and Bhattacharya 2017, long back. So these are the 4 samples. The left hand samples indicates the grain size from the core of the Pluton, whereas in the right hand side indicates the grain size from the marginal part of the Pluton. If you compare these two by visually, you can see the central part of the Pluton will have smaller grain size relatively compared to the marginal part, because if you can see in the central part the peak is at 5 micron. This is exaggerated with 10 to the power 2. This is 5 microns. Here you can see again this is 5 microns. The peak is around less than 5 micron. But if you see the marginal part, the grain sizes are mostly polymodal. You can see the grain size at 5 micron as well as larger 20-25 microns. There you will see a 10 more than 10 micron and more than 10 micron grain size. So from here we have a conclusion that the anothocyte in the central part has a different deformation mechanism compared to the compared to the plagioclase in the final part. But to study this point further, you have studied, and these are the microstructure from the annotocyte core. Now you can see the annotocyte core that is in the central part. Igneous texture is preserved. The igneous texture is preserved. This is magmatic plagioclase, and here you can see olivine. So this is the typical magmatic texture for gabbro basalt is preserved. Again, subgrain rotation is common where the two grain to grain contact is achieved. This is a microphotograph of the same. This is a strain-induced grain boundary migration. You can see a very small bulge, a strain-induced grain boundary migration. Again, a strain-induced grain boundary migration yields the grain-to-grain structure, which is the lowest temperature deformation mechanism of feldspar. And I have measured the anorthite content, which again shows that there is no great change in the anorthite content of the material, as there is no change in the, just a minute, there is a no big change in the anorthite content. We can safely conclude that the deformation mechanism is mostly due to the difference in the mechanical energies or mechanical properties of the rock, not driven, and it is not driven by chemical potential. Now, finally, this is a picture which shows the mafic minerals and plagioclase. Again, which shows that the most of the plagioclase in undeformed part is preserve the magmatic texture, but where the grain to grain boundary between these two feldspar grains is achieved, it occurs a variety of microstructure ranging from subgrain rotation, grain boundary stress induced grain boundary migration, and core mantle microstructure. And all these features are indicative of dislocation creep accommodated deformation. Now, if we come to the annotocyte margin, you can obviously see the grain size changes rapidly. First one is the pink. First one is the pyroxene, which shows a kink band, and the pyroxene kinking is a very important, very high temperature phenomenon, and it occurs mostly at temperature greater than 900 degrees centigrade. Again, if we see the plagioclase crystals, the plagioclase crystals roughly show an alignment. The best way is to see that the albite lamellae is mostly parallel. Now, there was a third one, there was a grain indentation. One grain is included into one grain is included within the other grains. And finally, chemical overgrowth. These are the microphotographs, because that time I do not have access to ACM. So these are the microphotographs, and all these features indicates that or indicate that the marginal part, feldspars in the marginal part deformed via diffusion creep. And you can see the grain, grain size, which is roughly 200 to 500 micrometer in size. That means wherever in the experiment people says grain size diffusion creep mostly occurs at grain size 1 to 10 micron. Here we provide a natural example that depend on certain conditions, grain size depend on certain conditions, feldspar may experience diffusion creep where the grain size is more than the experimental size. Now the puzzle. So what promotes the diffusion creep in the feldspar from the Pluton margin? Because usually these grains are large, temperature is 900 degree, this is high temperature. So what promotes this deformation? To do this, I did some geochemistry, and this was published in another Bulletin Geological Society of America paper. And I mapped a particular portion. You can see this portion. This is the south of the Bolangir. This place is known as Kamsara. Here, these rocks, which are marked as dark area, these are known as ferrodiorite, or we term this iron, titanium, zirconium rich rock, and these are the residual melts. In the fields, if we go, although most of the outcrops have been destroyed now, So there are a C fabric relationship, and sometimes it engulfs the anothocyte. It get part of the anothocyte, and it occurs as a dye. Now, what is now our my next step was to investigate what was the role of this male ferrotite for this anothocyte crystallization. For this, what I did is at first I assume, and I am not showing here the mineralogical simulation process. That is very long and it will be a different topic. So I modeled the feldspar anothocyte crystallization mechanism. After that, what I did is that I assumed that this is a Newtonian magma. I calculated the viscosity based on the Einstein-Ricci equation, where eta mix is the viscosity of the crystal magma, and these are the parameters of the liquid. Eta 0 is the liquid viscosity, and 1 minus phi s by phi m. These are the parameters, and minus k is the experimental result. Using this, we can have another equation: viscosity equal to stress by strain rate. So if we have strain rate, we can produce what happens here. Now this diagram shows the log 10 difference in the viscosity due to crystal content, and the x-axis contains the crystal liquid fraction. I'm sorry, it is not showing full here. So there is no crystal, 0, all liquid, and one is one is full solid. And there are other formulations of K, and there are scientists called Spera and March, which have given different values of phi s, the packing index, and the K, that is called the factor. And using these values 0.40, packing index 0.74, and 90, that means 0.40 means grains are very weakly packed, 0.74 means grains are roughly packed, and 90 means grains are mostly packed. And for the feldspar, this is the most common. 990 is the most appropriate because feldspar is tabular mineral and it can easily pack to one another. So using these two grains, we have computed the shear viscosity difference, and you can see if the magma content or the crystallization increases after 0.8, on all the 0.8, that means 80% of the melt has crystallized, the shear stress or the shear stress is going to infinity. That means the rock will not more deform So here, after this crystallization has happened, there is a porous crystal network. There will be some melts within the crystal that will be entrapped, that cannot be expelled out by any means. So with rheology structure, what I give earlier can be correlated to understand the melt migration and melt-induced migration and melt-induced deformation in the natural system. So to conclude that, I can say that first, this is the example where we can say larger than experimental size plagioclase crystals can exhibit diffusion creep, accommodated recrystallization, and it is finally the melt or the melt rheology where it comes to the geochemistry, controls the deformation nature of the plagioclase, and the geochemistry of the melts again, which is the residual viscosity of the residual melt that is trapped within the crystal liquid melt, promotes the diffusion creep within the feldspars, which are greater than 1 millimeter size feldspar grains, at least in the case of Bolangir Pluton. So this was my talk. As Dr. Jyotirmoy asked me to complete it within 30 minutes, I prepared in this way. And finally, I can say the most of the things are taken from Professor Talis and Professor Stuni's publication to summarize, as well as rock microstructure. And finally, I thank to my colleague, Dr. Jyotirmoy and Dr. Santanu Misro, my contemporaneous fellow from IIT Kanpur, for the invitation and their continuous encouragement, though I left this field few years back. So thanks, and I'm ready to take the questions.
Thank you very much, Dr. Nasipuri, for a very nice talk. And thank you very much, especially for taking us back to the classroom with your initial set of slides. So now I open the forum for questions and discussions. Please, you may raise your hand and ask your question. Yes, Ujjwal, please.
Yeah.
Sir, the part you said ki the 80% of mail is crystallized, the shear stress will go to the infinity. That part I did not understand, sir.
Yeah, if you go to the slide, let me go to the slide. Yeah, can you see this?
Yes, sir.
Yeah. So okay, what happened after 8? Once the melt fraction crystallization content is 80% is over, what happens? The Einstein-Ricci equation cannot calculate it. Okay, because the equation is framed in such a way that after that, if you take the log, it will be negative. And negative log is not possible. You can calculate it in your hand. Negative log is not possible, and so it will go to the infinity. Shear stress is going to the infinity in this way. So whatever is the rock which is produced into the porous material cannot be expelled by any other means. This was the point.
Okay, sir. So this is the mathematical model we are
Yeah,
talking
this
about.
is a mathematical model.
But if we talk about the what happens really in the nature, can we expect the same thing?
Yes, yes. In there are other annotocyte complex. If you see Turkel or Bhawanipatna annotocyte complex, or even Koraput annotocyte Pluton, that is very small although. You can also see the same thing. Melt bands are trapped within the annotocytes, and that melt bands cannot be taken out, because if you know there for I think Banaras in 1995 gave some thresholds, melt percolation threshold, liquid percolation threshold, melt escape threshold for the granitic systems. Similarly, for the mafic rock, or from the that is followed from the granite rock. Similarly, for the residual liquid rock which was rich in iron and titanium, we can calculate it from the viscosity. The background of this calculation is the MELTS software, which I have not discussed here, as that will be the little off focus from the study. From the some of the values, mostly the rheological values, the viscosity values, which you can see eta 0 is taken from the MELT software calculation, and then we put the Einstein-Ricci equation to find it out. It happens in nature. You can see our paper in 2000 that published in 2011. There was an appendix was given there, and the Excel spreadsheet was given there, so you can calculate it again if you want.
Okay, thank you, sir.
Ujjwal, can you introduce yourself, please?
Yeah.
Myself, Ujjwal Kumar Singh. I am doing my master's currently in second year from University of Delhi, and I hail from Varanasi, Uttar Pradesh.
Thank you, Ujjwal. So for next question, see if the person can introduce himself or herself will be great. Any other question? Professor, yes, Ayan, please go ahead.
Okay, sir. My question is, am I audible?
Yeah.
Yes, if you can.
Okay. My
introduce
question,
yourself once.
yes, I am on Patsa from Jadavpur University.
Hmm.
My question is, if you, as much as I know about this equation of Einstein-Roscoe, that this equation is only valid when the crystal content is quite low, less than 20 or 25%. So how can you use this equation when the crystal content is high, as you have
Yes.
shown the graphs?
Yeah. So if you see the original paper, I agree with you. The crystal content was low. That is 20 to 30%. But if you if you explore the literature, you will find there was some literature by Spera. I forgot the year, but I will tell you. And there was a literature by Mars 1981, who has modified the equation K's values, And I mentioned about one thing, if you remember, the packing index and the minus K values. So these can be extended up to 90 to even full crystallization if you use the Mars values and the Spera values. So what you are seeing here is the basics of the Einstein equation modified by Spera's observation as well as Mars 1981 observation.
Okay, thank you.
Okay, if you see, if you want to mail me, I will send you the references. You
Yes, sir.
can,
Please send.
yeah.
More questions? Professor Bose?
I think.
Professor Misra, any comment?
No comment.
So if there are no further questions, may I invite Professor Bose or Professor Misra to conclude the session with their vote of thanks and any remarks if they have? Okay. Seems. How about Professor Bose?
Yeah, thank you, Jyotirmoy.
Okay, Shayan has a question. Okay, Professor Bose, you go ahead and then we'll take science question.
Okay. I must congratulate Pritam. Very excellent deliberation. In fact, Jyotirmoy told correctly that you took us to the classroom with the old stuffs that we studied during our college days. And in fact, it's a nice piece of work to do. And most of the people we do with the quartz. And I think it is always better to try with different mineral that you have tried upon. I think this study should continue. And I think this could also inspire many people to work with feldspar deformation.
Thank you, sir.
So thank you very much, Pritam, for introducing this topic here in this forum.
Thank you, sir.
Okay, Shayan, you can ask.
So I was asking that the most of the deformation you are talking about is basically, as much as I have understand, is a subsolidus deformation process. I mean,
Yes.
yeah.
Yeah.
So now the deformation temperature or deformation grade, what we are getting from those microstructures or whatever, those are deformation temperatures or the crystallization temperatures, or we can, correlate the both in.
We can correlate the both.
Okay.
We can correlate the both. If you see annotocyte solidus curve, annotocyte solidus curve, there were a lot of experiment by John Longley. You can see that the annotocyte starts crystallizing at around 1100 degrees centigrade. Okay. Now, if the pressure is reducing, the system is like that. If the pressure reduces, annotocyte plagioclase accumulates much more.
Okay.
Okay, and the magmatic temperature, which I have not discussed again here, that is a bit of thermodynamics, is around 950 to 1000 degrees centigrade. But once you can see the magmatic features like orthopyroxene and plagioclase, you can easily conclude that this is an magmatic texture and the temperature is around 950 degree into 1000 degree centigrade. But the dislocation creep and the deformation mechanisms, which I saw for the from the core of the Pluton, is obviously relatively less deformation temperature, that is around 650 to 700 if you see the correlate with the books. But in the marginal part, again, ferrodiorite, which was liquid at that time, which indicates that although it was deformed, but the melts which was present at nearly 1000 degrees centigrade promotes the diffusion creep.
Okay. So, another question is like the features which you can see in microstructures as they are in the subsolidus phase in an pretty much higher temperature. So, is there any probability that it is basically due to the high temperature and not based on the deformation only, or the deformation may not be present and it is basically the temperature which is producing those microstructures?
Can you please repeat? I'm
For
not getting.
example, sir, there is a high temperature as we are seeing from those microstructures. So, is there any probability that the deformation has a lesser role and the temperature, the crystallization temperature, the higher temperature, that is not basically due to the deformation process, or deformation is not
No. If okay, I got it. If you have only temperature, then how could you define a fabric?
not a preferred fabric, but a particular.
But there is a fabric, but there is anothocytes are very large, grain size is very big. There is not a very preferred fabric, but in the diffuser there is a fabric. That means some sort of deformation was there. If only temperature, you cannot define a fabric.
Okay, sir. And a third thing I want to know that in subsolidus process, it is possible to go up to a range of recrystallization or full recrystallization in subsolidus process, or it is restricted to solidus deformation only. I don't know this. Actually.
There is I'm not getting. There is nothing called solidus deformation.
No, in subsolidus process, sir, is it possible to deform a grain or mineral up to recrystallization process, or it is only possible in solidus process?
Then what is solidus process? Can you just define that?
Solidus process, as much as I think that the solid when the whole rock is solid and there is no melt within that.
And then subsolidus?
Subsolidus, there is a combination of both melt and some crystallized grains.
So if this is your definition holds true, then then this is subsolidus process.
Yes, sir.
Okay.
Okay, sir. Thank you.
Okay, we will take the question from the chat in a moment, but before that, may I invite Dr. Sumit Kumar Ray to go ahead, please. Sir, please.
Okay, thank you, Jyotirmoy, and congratulations for a very crisp presentation. My question is that you said that grain size within the chamber, I hope the process was within a magma chamber.
Yeah.
It is larger in the peripheral part and smaller in the central part.
Yes.
Can you explain? Because why I ask this question is because the heat loss is faster in the peripheral part near the contact, because the heat loss is from the melt towards the wall of the chamber. Yeah. So heat loss is faster in the peripheral part, and there the grains will crystallize.
Yes, I got your point. Actually, sir, what happened once the annotocyte crystal mass is coming, moving towards the upper direction, this is called syndeformational features. So the grain to grain contact, what the grains which are maybe a larger grains which have already achieved grain to grain contact in the central part, during this emplacement they got deformed and they got recrystallized by subgrain rotation. So the original microstructure is very less preserved if there is any magmatic grain. I saw in that space that only 1 or 2 places it is preserved, but usually the grain size is very low, and that is that is due to the deformation process, recrystallization process. Now, if we come to the outer part, usually I agree with you, the heat loss is very high. But what happens if the heat material or a heat hot liquid is trapped within the grains? That is the ferrodiorite case. In that case, the rock will be the opposite case where the melt is there, and ferrodiorites are full of zircon, titanium, all our radioactive elements are there. So it has, apart from its magmatic heat, it also has another heat, radioactive heat. So in this way, we believe that the peripheral part, the heat was much more compared to the central part. Central part may have larger crystals. We have some small traces of evidences, but we cannot definitely conclude from the same.
Okay, okay. But the residual melt develops at a very late stage,
Yes.
after the main cumulate phases crystallize, and I think they mainly form as lubricating agent in between the crystals. They prevent the crystals from coming in contact and to deform. And I think okay, I have heard what you have said. I'll have to think over it, that
Okay.
whether the heat content or heat generation, rather, as you said, the uranium and other minerals, or they are heat generating minerals, maybe along with iron and titanium, may be higher in the residual melt part. So that's why.
Yeah, I can give you one information, because these ferrodioids have around 5,000 to 7,000 ppm of zircons.
Of what?
7,000 ppm zircon.
Okay, okay. Please, thank you very much.
Most welcome, sir.
So unfortunately, I got disconnected, and hence when I joined back, I can't see the chat window anymore, the messages that were written. So may I request whoever wrote the chats can, go ahead and speak and ask the questions? Can I just request?
Yeah, I can repeat.
Can you read? Okay. Then Dr. Nasipuri, please go ahead and answer those two questions.
Yeah. One question is by Dr. Prabhat. How is the recrystallization of olivine crystals in ultramafic rock differ from quartz or feldspar crystallization in felsic rocks in terms of paleopiezometry? So I'm not an expert in this, but what I did little work on olivine during my postdoc. So olivine crystallization is completely different, because olivine crystallize in a different class from those of quartz. So there is no such link for olivine piezometry in my knowledge. So if you can elaborate the question, then I can try to answer. And next question is Mohita. Say, is it true that annotocyte cause low impact on climate? I do not have any answer for this.
Okay. Any further questions? Any comment?
Yeah, I'm planning to reopen this work again, so any comment will be helpful for me also.
So Dr. Bose yes, please go ahead.
No, what I think Professor Mandal is there.
Yeah.
Professor Mandal.
Sir, if you have any questions or comment.
I am extremely sorry that I could not listen to Pritam over the entire stage, but this is a nice problem to work on. Of course, there are many issues. For example, I was not very clear in my understanding that when people are talking about deformation of solid crystals in crystal melt aggregates, the problem is this, that if the viscosity ratio between the solid component and the adjoining melt is more than, let's say, 10 square or so, then it's very difficult to deform the solid part. Okay, so if you are talking about the deformation of that kind of material in this magmatic system, you please look at that issue.
Okay, sir, I will look at it. Okay, sir, I will take your suggestion.
Second thing that I was looking at one of your slides the level of shear stress that the graph was showing, that is in the order of 10 to the power minus 16 Pascal or so, probably. Right? I could not understand that. Because in an earth system, we always have stress continuity. So even you are having melt or something, the stress continuity would be there. So can we lower the stress to that kind of extent? So this thing I could not understand what it actually means. So 10 to the power minus 16 means is void, right? It is a
These are
situation.
these are the computed results.
So these are the points.
Yeah, I will look into this. I will take your suggestion and I will look into this part.
Oh, sorry. Okay. Sorry, my microphone was switched off probably.
No, sir.
Sorry, I'm sorry. Okay, Pritam, I liked your talk. So I already, spelled all the points that came
Yeah,
to my
I
mind.
got your point, sir.
And the major point I would like you to take a special attention, deformation of melt crystal aggregate system.
Okay, sir.
The reason is this: when some crystals are forming from a melt mass, the viscosity ratio is in the order of several orders, like your 10 to the 10 square or 10 to the 5 or so on and so forth. Now, if you have this viscosity ratio more than, let's say, 10 square or so, it is very difficult to deform plastically the solid component.
Okay.
So here you are getting deformation in crystals. It is an interesting finding, but I could not understand that. How is it possible to deform in that kind of mechanical setting? This is one point that I had. And the second point is with regard to the stress level that you showed in these calculations. It was in the order of 10 to the power minus 16 Pascal.
Yeah.
This is the second point. And the third point was the consideration of the strain rate. 10 to the power minus 15 per second, this strain rate is applicable to the actually solid part of the Earth's lithosphere. Now, when you'll be going to any magmatic system, for example, if you go to mushy region beneath mid-ocean ridges or somewhere else, like your mantle wedge melt crystal mixtures, there, the strain rate is not as low as you are showing here, 10 to the power minus 15 per second. This 10 to the power minus 15 per second is applicable to only solid lithosphere.
Yeah, I take the data from searching the literature only from.
Yes. Like if you go to the Himalaya and you look at the deformation of Tibet, the strain rate would be in the order of that, 10 to the power minus 15 per second, minus 16 per second. But here, the strain rate would be much higher.
Okay, sir.
So these are the issues you can consider.
Okay, sir, I will do.
Okay.
Okay, sir.
But I like the topic, Pritam.
Yes.
And you spoke very well, very clearly. Very good.
Thank you, sir. Thank you, sir.
Okay.
Sir, any further question?
No, thank you, Jyotirmoy, and it is
sir.
nice to see you.
Okay, sir. Thank you, sir. Any other questions? Okay, if not, Professor Bose, is there any other point we wish to discuss right now, or we conclude?
Yeah, I think if there is no more queries, then we can give a big round of applause to
Yes.
everybody.
Yes.
And we can conclude.
Okay, thank you all.
Okay, thank you, Dr. Nasipuri, and thank you everyone for attending. And you will get the invitation for the next online talk soon enough. and I wish to see you all again back